Yeah, next one is, it's very important concept. Finding the focal length of a convex lens by lens displacement method or conjugate foci method. Conjugate foci or lens displacement method. Of course, for any lens, suppose there is a convex lens, and its focal length can be found by three methods. Number one, by distant object method. Distant object method means when the lens is keeping exposed to the sunlight, then sun is at infinity, the light is parallel to the principal axis of the lens, and after refraction the light rays are converges to focus point. Okay, therefore focus point to this lens distance is giving the focal length. This is distant object method. It is roughly calculated, which is approximate value. So here the focal length, approximate focal length of the lens. Okay. Now second method is UV method. UV method. What is UV method? So this is the screen and this is object. Say this is object. This is object, and a lens is keeping at a certain distance, say u distance, keeping at particular position u distance. Now the screen is adjusted to get the sharp image. Sharp image. Suppose the sharp image is obtained on the screen where the screen is keeping and its distance is measured, say v. Okay. So in this case, object and the lens distance, these two are keeping at a particular separation, finite distance, and the screen is used to obtain the image of this object. And which image? Real and sharp image is obtained on the screen, for which the screen is to be moved and screen is to be adjusted. Screen is to be adjusted in order to find the sharp image on it, right? So this method, suppose after finding this, suppose sharp image is obtained on the screen, the lens to the screen distance is image distance and object to lens is object distance, then focal length can be found by using, so 1 by f is equal to 1 by v minus 1 by u. So taking the sign convention, that is u is a negative, therefore 1 by f is equal to 1 by v plus 1 by u, and by simplifying this is uv by u plus v. So this is the formula to find the focal length of the given lens by UV method. This is second method. UV method is the second method. This is second method. First method is lens displacement, distant object method. Already given the distant object method, lens focus to the sunlight. The light is incidenting on the lens, that is parallel beam of light, and after refraction, so the light rays are come to focus, giving its image at focus point, and that image formed where the image is formed at certain point from the lens, that is taken to be focus point. From focus to the lens, distance is measured, which is known as focal length. So that is one method. And second method is UV method, in which the screen is to be adjusted till you get the sharp image on it. Then the distance of the screen and the lens is measured, that is image distance, and object and the lens already we fixed, that is object distance. Then using the lens formula, so f is equal to uv by u plus v, by putting these values, whatever you obtain on these values, then simplify it, you will get focal length of the lens. This is second method. And third method is, this one is third method. This is third method. Finding focal length of the convex lens by lens displacement method or conjugate foci method. Conjugate foci method. So let us see here, what is a conjugate foci method? Okay, but here in this method, object and the screen, these two are keeping at a fixed separation. At a fixed separation, we should not move this object, either object or this screen. These two are keeping at finite separation. So they are fixed and the lens is to be moved from object to the screen. Therefore it is said to be lens displacement method. UV method where the lens is not adjusted, the screen is adjusted to get the sharp image on it. Whereas lens displacement method, here the object in the screen, these two are keeping at a fixed separation, that is say capital D, the lens is to be moved from object to the screen. Therefore the lens is moving or adjusting in order to get the sharp image on the screen. Therefore this method is known as lens displacement method or conjugate foci method. Conjugate foci method. What is the meaning of conjugate foci? Let us see this. First of all, here the separation is capital D between the object and the screen, say capital D. But here this distance capital D must be greater than 4f, 4 times the focal length of the given convex lens. This focal length is, how we can find this focal length? This focal length is calculated by distant object method, already given the first method, which is known as approximate focal length of the lens. By that method, directly we observing by sunlight, we will get the focal length. So the light is focusing at a focus point or converges to a point which is known as focus point, then directly we are getting the focal length. In this case, that focal length is approximate value, approximate focal length. Okay, right? By taking approximate focal length, say example, suppose by this method we obtained a focal length say 20 centimeters. Then 4 into 20, 4f is equal to how much? 4f is equal to 80 centimeters. Therefore, the object in the screen, the separation must be greater than 80 centimeters. Say it is, you can keep them at a separation of 90 centimeters, 95 centimeters, 100 centimeters, whatnot, yeah, as you wish. But the gap between, the separation between the screen and the object must be greater than 4f. Why it is so? Why it is so? Why we are keeping that greater than 4f? For conjugate foci. What is the meaning? What does it mean? What does it mean? So here, whenever we are keeping the separation that capital D, which is greater than 80 centimeters, that is 4f, greater than 4f. Now the lens is slowly moving from object to the screen. As you are moving this lens towards the screen at one particular position L1, say, so here its clear and magnified image is obtained on the screen, which is sharp, and the magnified image is occurring on the screen at a position of L1 where it is marked, right? Now again further the lens is moved slowly, then this image, already magnified sharp image on the screen, that will be disturbed. Again it is blurred. As you are going further forward, then at some other position again you can find a very sharp and diminished image can be obtained on the screen at some other position, say L2. So you are getting here at position of L1 a sharp and magnified image is occurring on the screen. Whenever the lens further moved towards the screen at some other position L2, where the sharp and the diminished image will occur on the screen. So sharp and diminished image is finding on the screen. Therefore, the position is marked there, right? So here the image of the object, sharp images, two sharp images are finding on the screen at two different positions of the lens. At two different positions of the lens. Therefore, here if you feel this is U1 and this is one more distance, say it is U2. U1 and U2 means this is first object distance and this is second object distance. Therefore, there are two possibilities of object distances. for which we are getting the sharp images on the screen. We are finding sharp images on the screen. Therefore, so it is a conjugate foci. So again I will give its meaning, conjugate foci. Conjugate foci, in the sense I will explain more and more regarding this one. Of course here, so I am giving that u1 and u2, there are two possible values of object distances. At u1, at one position, image is sharp, obtained on the screen and magnified, and at some other point, that is u2 distance, object distance, where the sharp and diminished image is finding on the screen. Therefore, here there are two object distance for which the sharp images are occurring on the screen, right? So how we will get it? For this purpose, we should take d greater than 4f. Why? See here. Why? Question is here. Why d is greater than 4f? Yes, we will take its proof. Suppose if I am taking this as object distance, say it is u1 is equal to, say u1 is equal to minus u, and v1 is equal to corresponding u1 is equal to minus u, v1 is equal to image distance, from here to here it is image, from here to here object distance, from here to here image distance. This image distance will be capital D minus u1, that is capital D minus u1 means u. It is positive, sign convention, it is positive. Now using lens formula 1 by v minus 1 by u is equal to 1 by f. Okay, now substitute these values. 1 by v1 is d minus u, minus of minus plus 1 by u is equal to 1 by f. Now taking LCM, u plus d minus u by u into d minus u is equal to 1 by f. So u and minus u gets cancelled, and simplify this. So df, this is df, which is equal to du minus u square, minus u square. Remove this, no need of this one. Yeah, so this is by simplifying u square minus du plus df is equal to 0. This is quadratic equation. Right from this quadratic equation you can get u value. U is equal to minus b plus r minus, means d plus r minus root over d square minus 4 df by 2. Yes. So in this case u is equal to d plus r minus root over d, we are taking d common, d minus 4 f by 2. From this formula it is very clear why d is greater than 4f. So if d is greater than 4f, in this equation we can observe d is greater than 4f, then this square root value is giving positive. Therefore u values are real. U values are real. Real. And roots are occurring, and we can find its roots. Two values, that is u1 and u2. Say u2 is equal to d plus root over d into d minus 4f by 2. This is u2. u2, see here, u2 is greater distance, u1 is smaller distance. Okay, now one more distance is u1, that equal to d minus root over d of d minus 4f by 2. So this is a minimum distance of the object, initial position u1, and this is final position of the object, for which we are finding the sharp images on the screen. so that here d is greater than 4f, it is possible to get two square roots, that is u1 and u2. So two values are obtained because d is greater than 4f, it is real. Suppose d less than 4f is considered. What happened? D less than 4f. So under root negative value, imaginary values are obtained. Not possible. Okay. So that is not possible in this case. D is less than 4f. So this is giving imaginary. So here d less than 4f, it is giving negative value. Square root of negative value, it is imaginary. So it is not possible. And one more case, d is equal to 4f exactly. Suppose the separation is keeping, by this example, 80 centimeters. Because 4f is equal to 80, it is keeping exactly 80 centimeters. Then, so d equal to 4f, this is totally become 0. What happens here? Finally, you will get u is equal to d by 2. Means instead of two images, only you are getting only one image, that is at the mid position, but it is not at all conjugate foci. Okay? Not possible. This is also not possible to get the two sharp images which are obtained on the screen, which are finding on the screen. For this condition, which condition? For this condition, d equal to 4f, so you will find that d by 2. For this d by 2, so only one sharp image will occur on the screen. Not possible to get the two images at two different positions of the lens. Not possible in this case. And d less than 4f, it is imaginary giving. It is also not possible. These two cases are not possible. Only one case is possible, that is d is greater than 4f. Then definitely you can find the two sharp images on the screen at two different positions of the lens. These two different positions, corresponding positions, are said to be conjugate foci. Conjugate foci means, what is a conjugate foci? Means here there are a set of points. Listen carefully. There are set of points on the principal axis of lens where the object and the image distances are interchanged. Object and image distances will be interchanged, known as conjugate foci. Conjugate foci. Once again, there are a set of points on the principal axis of a convex lens where the image and object distances, or image and object positions, will be interchanged, known as conjugate foci. Why these two images are occurring over here? I will explain this conjugate foci. See here, suppose we can take this like this is object, of course, this is object, this is a initial position, right? This is final position. See, this is total capital D. Now this is the object distance u, and corresponding image distance is this one is v. So for the first position of the lens where the sharp and magnified image is obtained on the screen at this position, and further lens is moved towards the screen at some other position where one more sharp and diminished image is finding on the screen. So this is the final position of the lens where this becomes object distance u and remaining this becomes image distance v. See here, this is object distance, this is image distance at first position of the lens. At second position, and this distance from the screen to lens is taken to be object distance, and this will be image distance. They will be quite interchanged. The positions of the object and the image, these will be interchanged. Means earlier this is object for the first position of the lens. For the second position of the lens, this becomes object and this image, like that. So here a set of points on the principal axis of a convex lens where the position of the object and the image will interchange are called conjugate foci. This is the meaning of conjugate foci. So clearly I was explaining this in detail, that conjugate foci in the sense what is the meaning of it. And one more point, why we are taking a D, why D is greater than 4F. We are raising a question why D is greater than 4F. For that I was given a clear proof. Otherwise, other two cases are not giving the conjugate foci, two sharp images. Only for this case, we are getting two sharp images at two different positions of the lens where object position and image positions will be interchanged, so that it is called conjugate foci. Therefore, this is all about the lens displacement method, and some more additional points are also there. I am going to derive them, and I was not finished this focal length, how we are finding. Actually, the question is finding focal length of the convex lens. It was not over. Actually, it is over up to why the D greater than 4F. Its cause, what is the reason, that is clearly proof is given. And what is conjugate foci? So this is in detail explained. Then go for finding the focal length of the lens. Now let us find the focal length of given convex lens by lens displacement method. So already we discussed that it is a conjugate foci method. It is conjugate foci method, means the distance of the object and distance of the image, these two will be interchanged. These two will be interchanged. The distances will be interchanged. So that is conjugate foci. Now here, this is object. This is the first position of lens. This is second position. This is U. And at first position V is this one. And at another position, second position is, for this screen act as object and corresponding object is image distance. So U and V, these two are interchanged at other point. Okay. Now here, what is the distance between screen and the object? Capital D is equal to U plus V, and X is equal to V minus U. How? From here to here, from the first position here to here, V minus U, you will get X. V minus U, you will get X. Therefore, X equal to V minus U. Right? Go for focal length formula. Yes, we know focal length, that is UV method. Focal length formula is UV by U plus V. This is focal length formula for UV method. UV method we discussed, that is second method to find the focal length of the lens. Right? So this can also be written as U plus V whole square minus U minus V whole square by 4 into U plus V. If you expand this one and simplify both, then you will get 4UV in the numerator, U plus V whole square, A plus B whole square minus A minus B whole square equal to 4AB by 4 U plus V. 4 gets cancelled, again you will get same. See, U plus V whole square minus U minus V whole square equal to, after simplifying, expanding, 4UV obtained by 4 into U plus V. What you are getting again, you will get same. Whatever the formula you started with it, the same formula you are obtained by simplifying this one. But as we know that, so here U plus V is equal to how much? Capital D. U minus V square is there. Either U minus V, V minus U, doesn't matter because there is a square. Therefore that equal to X. Put this instead of U plus V capital D, U minus V, X. Then you will get D square minus X square by 4D. Yes, this is the equation for focal length of the given lens, or otherwise we can write over here focal length f is equal to d square minus x square by 4d etc. So this is the formula for focal length of a convex lens by lens displacement method. Lens displacement method and some other supporting points. If you go in detail, then you will get some other points. So let us see them. So M1 magnification. Magnification whenever the lens is at a position L1. At position L1 magnification formula M1 is equal to V by U at position L1. Okay. So whenever the lens is at a position L2, some other position where the image is sharp and diminished, where the magnification M2 is equal to here U by V. This is image distance U by V at position L2. Now M1 into M2, their product is giving V by U into U by V gets, these two gets cancelled, these two gets cancelled, you will get 1 M1 into M2. The product of the magnifications of magnifications at two different positions will give 1 its product. It's proved, okay? It's very clear. Now, so M1 is, can we write like this, size of the image by size of the object at position L1. M2, size of the image by size of the object at position L2. Of course, sizes are different. So at first position magnified size, at second position diminished size. So I1, I2 are different. Now M1 into M2 multiplied, you will get M1 into M2 is already proved that 1 is equal to I1, I2 by, so O square, that is O square is equal to, O is equal to root over I1, I2. So O means size of object, size of object. I1, comma, I2, size of images. Size of images. So this is one of the very, very important relations. Okay. So again, let us go for another relation, which is, see, when we consider the first two conditions, that D is equal to U plus V, D is equal to U plus V, and X equal to V minus U, and simplify this, solve them, these two gets cancelled. D plus X is equal to 2V and V is equal to D plus X by 2. Okay, and similarly, subtracting from each other, D is equal to U plus V and X equal to V minus U. Subtract them, minus, this is plus. These two gets cancelled. D minus X is equal to 2U and U is equal to D minus X by 2. So you are finding that image distance is D plus X by 2, object distance is D minus X by 2. These two are obtained. Then afterwards, so we can also find one more relation. What is that? Here the product of magnifications giving 1 and division of magnifications we can also find from it. So let us see that division of magnifications. Of course, this is X equal to V minus U. Keep them aside. Right here, M1 by M2 is equal to V by U by V, which gives us actually V by U by V. Their ratio is giving V by U whole square, which gives us V is D plus X by 2 by D minus X by 2 whole square. So which gives us then M1 by M2 is equal to D plus X by D minus X. This is also one of the important relations. Okay. So important relations are the product of magnifications giving 1, here one more relation is size of the object is equal to square root of product of size of the images at two different positions of the lens. And third relation is m1 by m2. The ratio is giving d plus x by d minus x. Then we can also get one more relation. So let us go for one more relation, that is m1 minus m2. Yeah, next relation is m1 minus m2, right? So here, as we know, d is equal to u plus v from the diagram, x equal to v minus u, and this is also from the diagram, and the magnification at the position of lens L1 and the position L2 magnification u by v. Okay, m1 minus m2. Clear, v minus u by v by u minus u by v. Therefore, m1 minus m2 is equal to, so cross multiplication or taking LCM, v square, taking LCM, v square minus u square is equal to uv, right? This is simplified, m1 minus m2, which is equal to, see, a square minus b square, a plus b into a minus b, v minus u into v plus u by uv, and m1 minus m2, which is equal to, so this is v minus u is how much? This is x, put here instead of v minus u, x by, this is taking down, this is u plus v. What is this value? Focal length. Therefore, m1 minus m2 is equal to x by focal length. And finally, the focal length is equal to, in terms of magnifications, x by m1 minus m2. This is your final relation. Focal length equal to x by m1 minus m2. Okay, this is also very important relation. Let us go for an example problem. So already we finished 8 problems earlier. This is the 9th one, problem number 9. Now this problem is related to lens displacement method or conjugate foci method. Now the object and the screen both are at a separation of, these two are keeping at a separation of 100 centimeters. And a convex lens is giving its real image, sharp image on the screen at positions, either positions of 40 centimeters apart. Now, it is at a position of 40 centimeters apart, so which produces a sharp image on the screen. Then find the focal length of the convex lens. See here, so this is x given already and this d given. Therefore, formula f is equal to d square minus x square by 4d. So this is a focal length formula for lens displacement method. Now f is equal to, capital D is 100 whole square minus 40 square by 4 into 100, which gives 10,000 minus 1600. Okay, this is 10,000 by, this is 400. Then by simplifying this, f is equal to 8,400 by 400. 0 zeros cut after simplifying, which is giving 21 centimeters. So this is the focal length. This is the focal length of the lens, focal length of the convex lens. Whenever it is giving the sharp images at either position of the lens 40 centimeters apart, then separation between the screen and the object is 100 centimeters. So this is the focal length of the lens. Okay.